Hi, this video should be about behaviors, more specifically about ALICA behaviors. So what can I tell you about it? At first you need to know that ALICA tries to be domain independent, and from this point of view ALICA handles behaviors as an atomic entity which is domain specific. So every behavior that lets your robot do something is specific to the domain where the robot is acting in. Therefore, ALICA does not divide it, so behaviors are atomic. And yeah, what else? Behaviors are the things that you can put into states of ALICA states here. So this is a plan, but all these here are behaviors. And yeah, we are here in the plan designer. What makes a behavior inside the plan designer? A behavior is represented at first on your hard disk by an .beh file, which is often a short XML file stating a lot of key value pairs of your behavior, like the name, where it should be generate its C++ code into which folder, some derived key values which are not relevant for behaviors, like whether it's the master plan, the utility threshold, another destination path in here. But what is interesting for behaviors is the frequency. This is the frequency, how often the run method of a behavior in C++ is executed. How long it is deferred or delayed before the first time it has to start, and whether it is event driven. So either it is event driven, for example you receive a new image from the camera, then trigger this behavior, or it is triggered by a frequency 30 times a second. Okay, what else? Yeah, it has an ID, and what you see, this is the behavior, and each behavior has a configuration, or it actually has several, at least it can. This is represented in the GUI in this repository view. A behavior is the red one, and a configuration is, for example, this default intercept. You can have several configurations for one behavior. Typical application is drive to point or something like that. Let's see. Yeah, here you can see drive to point drives to point, obviously, but these different configurations drive to different points, and the difference is in the parameters. Here you can see it's simply a key value. Both are strings in the plan designer and interpreted by C++ into a name and a number, coordinates in this case. So drive to point default drives to the coordinate -2200 and 0, and as the name states, 0 2000 drives to 0 2000. And what you can see here, it's in let's see, it's in plans generic behaviors, drive to point, and here you can see that it has several configurations and the two parameters x and y for each configuration. So now you know how the matching from the GUI to the XML file works. Okay. So when you have modeled a behavior here and have done what you have to do, like the parameters and all these configuration things here, you can adjust. You normally auto-generate some code for the behavior. What is happening there? Let's see. Yeah, here. Eclipse. We have, for example, the intercept behavior. So it is generated into the same folder. Source, plans, behaviors, inside the MSL expressions package. That's because it was located inside plans, behaviors, intercept BEH. So it's the same structure, but now inside the expression validator project. So MSL expression auto-generated, and then source and so on, as we saw in in our Eclipse. And what is auto-generated is actually at first a complete stub, or a class with a lot of stubs, like the constructor. Let's go through the header. It's actually the HUD, the constructor, destructor, the run method, the initialized parameter method, and that's it. The rest is programmed and added by hand, by yourself, inside the protected regions. Anything you program here which is outside the protected regions will be deleted when you auto-generate the source code again. Auto-generation, as shown in other videos, is done like this. Okay, finish. Here it moves a little bit because we auto-generated again, but everything in a protected region remains here. So if you want to add some protected things, use this protected regions, private here, public there, includes or forward declarations here. The same goes for the content of the auto-generated methods. So we have a constructor, and inside we have a protected region. Destructor, inside protected region. Run method, inside protected region. And also for initialized parameters. And if you want to implement other methods, do it inside here. Okay, what methods did we mention? Constructor, initialized parameters, and run. So inside the constructor you normally initialize some configuration values like we do in the intercept behavior. Here we read the max ball velocity or the catch radius from some config file, drive intercept max ball velocity, and we do it only once because the constructor is only executed one time during the startup of our base process, which includes the ALICA engine. So put anything here which you only need to do once for the complete runtime of your base process. The next step you can think about is what you have to do in the initialized parameters method, because this method is called every time an agent enters the state where the behavior resides inside. So every time an agent is executing some other states here and then going over some transition into the state getBall and will start to execute the intercept behavior, therefore it will execute the initialized parameters method one time. You can see here we reset our PID controller for the next calls of the run methods. So we reset the distance error, like the D part of the PID and the I part of the controller for distance and rotation. So, and what does the run method? This is the method which is called, for example, 30 times a second when you choose to configure it that way, like here, 30 times a second. The structure in a run method, at least there is some recommendation. At first you should acquire all data you need to make your decisions in the run method of your behavior. So in this case we need our own position, and if we don't get it, don't make any experiments, just return immediately, or in this case we drive 50 centimeters randomly around because we try to relocalize ourselves, moving away from this dead spot we are currently sitting on with the robot. But the more clever method is to just return and don't do anything in a behavior where you don't know where you are, at least in RoboCup. robotic soccer. Next we need to know the ball position, and also here we return, and we need the corrected odometry data, and if nothing of them is available, return. Then the ball velocity, if we don't have it, set it to 0. So for this behavior it's okay to don't have a velocity, but if we have a velocity, we adjust it to the maximum velocity we assume in this behavior, and now we are done. Here we declare and get everything we need to calculate and make decisions in this behavior. The next things you do is some calculations, some extra cases, and here we predict the ball and so on, and at the end we try to get some path planning advices. For example, where is it? Get ego. Here. Get ego direction from the path planning proxy. Hand over your target point and get the result back. And with the result, do some adjustments. And at the end of every behavior, you should, or almost every behavior, you should do something like sending an actuator message to the rest of the framework, to some drivers. For example, here we have the motion control message, and we fill it. We have in the motion angle, translation, and rotation. Here's the PID controller for the rotation. Rotation is set here. And then we simply send this message to our drivers. In this case via ROS. We have the send method here. Let's see, the sender ID and the timestamp is added. We cut the max translation for security issues and publish it. And what we also do automatically is here sending or remembering the sended motion control message for having a history of our control messages. Okay, but this method here is not part of your implemented behavior. It's part of the domain behavior, which is part of the hierarchy of classes. So let's look at this. Every behavior which is auto-generated is in the namespace ALICA because it's an ALICA behavior, but it also inherits some things from the domain behavior. Let's see, what is this? The domain behavior is already something domain specifically because it's providing some send methods for actuator messages. So this is our message for sending move commands to our motion. Ball handling, kicking, shovel select, pass messages, watch ball messages, debug messages. And we also provide something every behavior, almost every behavior needs, like the robot class and the world model class. World model for receiving or getting data from the environment, and robot class for something that helps you to create these motion control or actuator messages, like moving the robot, kicking, and so on. So this is some helper, basically, both. Also the system config for loading configuration files, and so on. Here are the publishers. So this is an intermediate class for domain-specific things every behavior in the domain probably need. And the basic behavior is the behavior which has everything that ALICA dictates to have, like let's say a name, a set of parameters, because the plan designer told us to put some parameters here, or at least it gives us the opportunity, the possibility, I mean. So with this method from the uppermost class, the basic behavior which is inside the ALICA engine, you see, you get some set and get methods like stop the behavior, start the behavior. But all this, you, except for success and failure, you probably don't have to call, because this is more or less done by the engine, ALICA engine. Okay, that's about the hierarchy. how the run method is implemented in these three phases: get data, make decisions, send the actuator messages. Yeah, I think that's enough for the introduction. Thank you.